Hello, welcome to a top secret location in the Center of Quantum Technologies in NUS. I am Jianwei, and he is Flo, yeah. And so we are very excited today to show you some of the exciting equipment that we have here. Like for example, advanced armor, right, which we did not develop, so I'm gonna put that aside. And stuff that we use in the lab to send signals and measure signals of specific frequencies that address atoms, because to drive them you need to drive them at a very specific frequency, otherwise they will not respond. So right now we have here two pieces of equipment which Flo will show you what they do.
Okay, so as Jianwei said, for experiments we need a lot of devices, and the two main devices you'll find everywhere are the oscilloscope, which is a device which can read a signal, and the function generator, which is a device which can generate a signal. So for example, if you connect the two of them with this cable, which is called a BNC cable, and you just turn the function generator on, you see the signal appear on the oscilloscope. So now, this is one measuring device, but we could use another device to measure. So what could we use to measure a signal? So for example, I have another one right here, and these are speakers. The problem is, how do you connect a jack plug to a BNC cable? Because there won't be an adapter for like everything in your life. So at some point, you need to make it. And that's what we're gonna do now. Okay, so here are the two cables we need. So one BNC cable adapter, and this is a jack. So when you open it here, so you can see on both devices, so for example, if you take the jack plug, the big part is the ground, and then you have like two connectors for the left and the right audio, the right speakers. And for the BNC, you have the ground here and the positive, where the current flows. So basically what we need to do is to connect the grounds together using a cable, and then we'll need to use another cable and to split the power input from the BNC to the two channels in the jack plug. So basically, and after that we just solder everything together, and that's the end results, and that's what we can use to speak to a speaker using a BNC cable.
Hello, yeah, welcome back. So it turns out that the speaker is not really a measurement device. It's actually called a transducer. It changes electrical signals to sound. Yeah. Whereas oscilloscope is really considered, formally it's considered a measurement device because it turns the signals into measurement that gives you a number that can process and so on. Yeah. So just to get it out of the way, right?
So yeah, so now that we implemented the adapter which is designed, let's turn the function generator on and see what it does. So you can see for 600 Hertz signal, you can see the signal on the oscilloscope, and you can hear a sound. So now, what if I change the frequency of the signal? So let's go up. So you see that when I increase the frequency, the pitch gets higher, and the signal on the oscilloscope goes closer together.
And the amplitude, I guess.
Oh yeah, and another thing is, wait, let me decrease this a bit. So the amplitude, so we saw that the frequency is directly related to the pitch of the sound, and if you modify the amplitude function generator, you will modify the intensity of the sound that you're hearing, which also increase on the oscilloscope when you have the amplitude of the wave grows.
Yeah. Cool. So so one curious thing is to, I don't know, I just had in mind is to figure out how sensitive our ears can be. So this guy is at 700 Hertz. So it turns out that your eardrum is vibrating at 700 times a second. 700 times. Can you do something 700 times a second? I can't, right? So so the eardrum does that. And now the question is, how often or how small a frequency change do you think your ear can pick up? So let's try that. Now it's 700. Can it be 701? 2? So changes of 1 Hertz or so, you cannot really pick up, right? But if you go up to 5, 10, you start to pick up a little bit, right? Yeah. Yeah, something like that. So now the question is, who does this help? This question, right? This little what's the sensitivity of this ear, right? So you figure that out yourself. We are just here to have fun, but sometimes fun things like that turns out to be useful, right? So yep, we hope you had fun.
So now for the next step, here we modified everything manually, but manually changing the parameters on the device. But in our setup, most of the time we do things remotely using a computer. So that's the next thing we're going to do here. We'll try to talk to the function generator using a computer. Okay, so now we just connect the function generator to the PC using a basic USB cable. So here, and what we did, we just wrote a basic Python script, and we just run it using the terminal window. So you can see, I'll play it one more time here. You'll see the frequency in the function generator will change, and of course the signal in the oscilloscope as well. So now, this is a really basic example, and what if we do something a bit more complex?
Yep, that is quite impressive. Yeah, so yeah, let's move on. So why are we showing you something like this? So what happens is that in the lab, sometimes we have to conduct experiments very quickly, several times a second. So for example, to address an atom, right, sometimes we want to use a certain laser frequency, and then to prepare the atom for experiment, and then later on we address it at a different frequency to probe the atom a specific way. So we need computers to help us. We need to talk to them via the USB, because we need to control the experiment not just a few times a second, but maybe several thousand times a second. That's why we are showing you this. That's why we have this capability, and it can be very easily coded with Python. Yeah. So just for a quick fun section, so this particular function generator, right, you can create waveforms of various shapes: a sine, square, ramp, right, and so on. A sine wave looks like this in your textbook, right? A sine, your nice curve. A ramp looks like a triangle waveform here. So right now we're gonna produce two sounds, one made by sine and one made by a triangle, and see whether you can tell the difference. Okay, so first is the sine. Okay, so you saw all the smooth curves, right? Different frequencies, but still smooth curves. Okay, next is triangle. Yep, so just now was triangle. The downslope was not very clear, but the upslope you can tell that it's a triangle, right? So what is the difference that you hear, and why? Right. Hey, so right now we're going to show you a very cool experiment, which has application, by the way. So the application is called Heterodyning. You can go online and find Heterodyning. But the basic idea is we want to measure something at a very low frequency, but we can only do the experiment at a very high frequency. So how do we do that? So for example, here we have a source that is at 440 Hertz, right? And the other source is at 442 Hertz. So in the previous video, you saw that 2 Hertz, your ear cannot really pick up anything. But what we're going to show you right now is that, let's say I on this 440, right? Okay, I'm going to switch it off. I'm going to on the 442. Also cannot hear a difference. Now what is going to happen if I on both, and both signals are being added on this very simple circuit board here, and it goes here. So what happens if I at both signals, 440, 442. What do you think will happen? 440 on, 442 is on. So you see, you can actually hear loudness and a softness that goes at about 2 Hertz, 2 times a second, right? And this difference is actually measurable, despite the fact that the sources themselves on their own were not distinguishable by your ear, right? So this is a basis for a technique, again, it's called heterodyning, that we often use in the lab to probe atomic systems that respond to very high frequencies, but we want to be able to measure their signal at a lower frequency. So it's called heterodyning. It's part of that. It's part of heterodyning. It's not the whole thing. The other very simple application that you find that uses this technique is actually guitar tuning. You can tune two strings that are very close in frequency together, but you want to get it exactly the same, you can use this technique as well. So you can go online and go and find related videos.
So now that we have a second function generator, we could play some more elaborated piece of music, like this classical piece that I hope you will recognize. So it's a really famous piece. I'll give you one clue. It's one piece from Beethoven. Yeah. So now I hope you'll guess it.
I thought it was in a Disney movie, but it's okay. But anyway, we hope we found the music soothing, the physics enlightening, and right, I think for the next sequel, we will kind of show you how this works, but that's the next sequel, yeah. So we hope that you like the tour, that you were scenic, and we will see you next time.